thanks. Good morning, day, whatever. I actually suggest everybody to turn on web cameras because I find it easier to talk when I can see people, not black rectangles. But anyway, okay, can you hear me? And can you see
Yes, yes.
our whiteboard? Okay, great. So I think our goal for today is to discuss solutions of some problems. I think we will go like this. We will start with 2A. So there were some difficulties we saw in your submissions. Then problem number 7 and problem number 9. And probably if we will have enough time, I want to discuss maybe problem number 16. So that's our plan for today. Probably we will start with, okay, we'll start with problem number 2A about geometric, sorry, okay. Geometric, oh, come on. Geometric probability. So let's recall the process from problem 2A. We have a stick. We choose a first point at which we will break the stick randomly. Oh, let's say here. And then we have two parts. And we choose one of these parts with equal probability. Let's say we chose the second part, and then at this second part, which is the second point at which we will break our stick, and then we try to form a triangle. If we can, it's a win. So, okay. Is the process clear? Now I will show a solution. It goes like this. So let's identify our stick with a line segment from 0 to 1. And now when we choose the first point, it's like choose a number from 0 to 1 on our line segment. Let's call it X. Yeah, and what to do next? Next we have two halves, or not halves, probably two parts of our line segment. What to do next? Do you have any ideas? Well, basically we want to construct somehow a phase space. In this case, we call it a sample space, because we talk about probability. So I'll remind the main idea of using sample spaces. So you have some outcomes, a set of outcomes. And there is an infinitely many outcomes. So there is an infinitely many points on a line segment. And it's hard to work, it might be hard to work with such sets. Well, because, well, probability of choosing one point equals to 0 because there are infinitely many points. So what we do is we identify it, well, with some shape in the plane. And then let's say that we have this set, this small set A, is the event, and we want to count the probability of this event, and this transformation leaves us with the following task to find an area of this set A, and then the probability, or let's call this bigger set X. So then the probability of A happening equals to area of A divided by area of X. So that's the main idea. So do you have any ideas to how to work out, well, how the shape for our problem will look like? Because I will tell you in like a minute. So if you have some suggestions, please tell us. Okay. So I suggest the following process. Well, as you can see, we have two parts now. And let's identify each of these parts with its own segment from 0 to 1. So this is red part, and this would be green. So each part of the stick is identified with its own copy of the segment from 0 to 1. And now let's see how the sample space would look like. So this is X. Okay, I'll draw it in black. This is X. So it's the first point. And I'll draw two copies of that. And here is, well, let's say we choose here point Y. So here's Y for the first part. And here's Y for the second part. And we get two squares, two unit squares, as you can see. Well, the process of breaking the stick this way actually identified with the process of throwing points in that two squares. Each square is chosen with equal probability. So let's say our point, random point, gets here. So what does it mean for our stick? So it means that we should break it. The first breaking point is here. So let's draw it. Okay, I'll draw a new stick. So this whole stick is identified with this line segment. We should break it here. This is our first point. And then let's look at the Y coordinate. Because we choose the second part, it's the rightmost part. Let's see, we identify this part with the line segment from 0 to 1. And well, the second coordinate is about here. So then we project, just scale this line segment from 0 to 1. And in this case, I guess it's about here. So that's our second point. If my point in the squares were in this half, in this right square, then I would choose it on the leftmost part. So is this process clear? Please ask any questions now. Oh, sorry. Okay, but now what we want to do is we want to draw some shape in this square, which will correspond to the event we want. That is to the event when we can form a triangle from a broken stick. So we want to understand how this shape looks like and what is its area. So let's try to do this. Okay, I'll probably erase some pictures so I could have more space. Okay. So let's see. What can we say about position of the first point? Suppose we choose a point in the first half. This is the first half. This is the second half. Well, not half part, but you get it. So then a triangle can be formed if x is more than 1/2. Is it clear?
Yes.
Yes.
Okay. And then what about y? We need now some restrictions on y. And if we choose y here, then the length of this little segment is y multiplied by x. And well, it's not quite right picture because actually what I need to draw is I need to scale this part to the line segment from 0 to 1. Here is y. And to form a triangle, it should be less 1/2. And also we have this little line segment here. And for this line segment, I think I should write an equation also. Well, I guess it's 1 minus y multiplied by x. Yeah, and this also should be less than 1/2. So as you can see, I have a system of equations. And now let's draw it. I probably should use something like this. Okay. So this is a line x equals 1/2. And then these two lines correspond to, well, the last two equations. And an area we are interested in is this one. And we can do the same thing for second part. And their shapes would look like the first one, but it would be like in a mirror reflection, as you may see. But it's the same shape. So now what we need to do is to calculate, well, area of this shape. And to do so, well, we told you that there might be some, well, integration. So if you don't know how to calculate integral of something, don't worry. So basically what we have is, well, suppose we have a plot of function, let's say 1/x. And you want to calculate an area, let's say of this shape. So here is point A, here's point B, and you want to calculate an area under this plot. So what you need to do is you need to take integral of 1 over x from a to b. Well, it equals to something like natural log of, well, b minus natural log of n. Is this notation clear in the right-hand side of our equation? Because I'm not sure if in English-speaking countries it's the same as here.
I think they write log of b minus log instead of ln. They write log. It doesn't matter because it's a function log.
Okay,
so
I'll write that ln of x equals to log x e here. Okay, to be clear. Okay, so this is the solution of a problem number 2a. Do you have any questions? So the main idea is the following. You have to scale each of the parts to the segment from 0 to 1, because when you choose a point arbitrary on a line segment, that's the process you opt for. So some students suggested the following picture. So they drew like, this is for first point x, and then for point y, they drew or something like this. So for each x, the segment is of different length, but then there is no like these points, or let's say these two areas, if they have the same area, it doesn't mean that they have equal probability. Because like Andrei showed for Bertrand paradox, the density of points of outcomes actually is not even in such a picture. So that's why you should scale your parts to line segment from 0 to 1. So
yeah, the scaling is the important thing, but here we does not obtain an answer. We doesn't compute this answer directly. We just say what you have to do to obtain it.
Yeah, so I think that I showed you how to calculate an area under this plot. But to calculate this area, let's see, we should take an integral, well, what's that, from 1/2 to 1. Here is 1/2, here is 1. I guess it's something like 1 over 2x minus 1/2 or something. It should look like this. If you know how to integrate, how to find such areas, there would be no problem to calculate these areas. But the main idea is to understand how these areas look like. So integration is just some minor technical part. Okay, so moving to the next problem. And as I promised, okay. The next problem would be problem number 7. And there is an important idea to solve this problem. Well, let's see. Suppose we have a unit sphere, the center. And we consider a set of great circles on that sphere. So this means here is an example of a great circle. It has center equal to the center of the sphere. And we want to operate in this set of great circles. But it might be quite hard because how can you well define a random great circle in a sphere, for example? How can you choose it? Well, I suggest a phase space approach. Let's see. Suppose we have a great circle, some great circle, and I want to identify it with some point on a sphere. Let's see how to do it. Well, probably, what can I do? I can draw a plane passing through this great circle. And then I can try to find points on our sphere which are furthest from this plane. Well, obviously, it's this point and this one. So if I draw a perpendicular line to this plane, so basically this is the points of intersection of that line with our sphere. And I want to say, well, let's call this great circle omega. It's Greek letter, I guess. Let's say this is point A. This is point minus A because it's like antipodal points. And I'd say that I have transformation delta. We call it, well, duality. This idea comes from a projective duality. I'll probably talk about it a bit later. And let's say that delta of omega equals to plus minus A. So this transformations, well, transforms our great circle into this pair of points. And actually for each antipodal, for each point, I can construct a great circle. Let's see how. Suppose I have some point on my sphere, and the next thing I do is I draw a radius, and then I draw a perpendicular plane to that radius, such that it passes through the center of the sphere, and then I draw a great circle lying in that plane. So in this case, I will write delta of A equals to omega. Is it clear how to, well, let's say, draw a dual great circle for some point and how to draw dual points for some great circle? And actually, this helps us this way. Now, the set of great circles on a sphere correspond to just a set of points on a sphere, and it's easier to operate with points than with the circles. And I guess we'll need some properties of this transformation. Let's see. Suppose, okay, I'll draw another one, unit sphere. Need a lot of them. Suppose we have some great circle omega and a point A lies on this great circle. So I'll write it like this. A lies on omega. And now let's see, can you guess what will happen with delta of A and delta of omega? Just clear some space to draw it.
So what can we say about the dual of this point and about the dual of a great circle if we know if the point lies on the great circle? Any ideas?
Okay, I'll probably move this point a little bit higher, so it will be easier for me to draw.
This duality is a hard concept from projective geometry, and if you find it out, you may discover some properties of this concept.
Okay, now
Is the definition clear, maybe, or not?
Please say something. Okay, so
Oh,
we want
it's
to understand
clear.
how.
Yes, yes, it's clear.
Okay, so now I'll just, well, at first I'll draw a great circle dual to a point A. So this is the radius of the sphere. And now I need to draw a perpendicular great circle. Okay. Something like this. So this is now delta of A. And now what I need is delta of omega, and delta of omega is two antipodal points. Let's see. So I need to draw perpendicular to a great circle omega, and then I obtain, well, this point and this point are delta of omega. And as you can see, it is very easy to prove that they actually lie on our delta of A. So this duality transformations just turns over this sign. So before we had A lies on omega, and now we have delta of omega lies on delta of A. So that's a very nice property. Is it clear? Please tell us.
Yes.
Okay, now to problem, I think 7a. Let's see how to solve it. There is a polygonal curve considered in this problem. But for simplicity, let's say that we have just one arc of a length p.
Maybe we should start with only one point.
Oh yeah, of course.
Instead of arc.
That would be simpler. So yeah, suppose we have just one point. How to find well, a great circle which doesn't intersect that point? Any ideas?
We want to parameterize all the great circles which does not intersect, doesn't contain this point, or which does contain.
So yeah, we can parameterize
all points on great circle of this point will their dual great circle will intersect this point.
Okay, yeah, let's draw. This is okay. Let's call this point A again.
Right answer.
Yeah, this is delta of A. And if I choose some point B on the circle delta of A, then its great circle delta of B will definitely intersect our point A. Okay, I'm sorry for my messy drawings. Yeah, okay. Let's clear up some space. Probably let's consider line segments now. And we learned to construct great circles, to parameterize great circles which intersect a point. We want to do the same with an arc, let's say of length pi times t, where t is from interval from 0 to 1. So it's a fraction of pi. So what's the process of parameterizing great circles intersecting in this arc? Well, actually, we need to do this procedure for every point on our little arc. So what we do is we take a point and we draw a great circle, and we take another point and we draw another great circle. So suppose this great circle corresponds, so this endpoint corresponds to this great circle, and this endpoint corresponds to that great circle. And then all the points inside our arc will be transformed into great circles between these two. So it's like a spherical segment, like a piece of a peel on an orange.
And what is the point when all these great circles intersect? I think this pair of points is dual to the extension of our little arc.
Yes, exactly. So they are due to, well, this great circle. I'll just extend our little arc in both ways, and these points are due to that circle. Okay, and by the way, what is the area? What is the area of these spherical segments? Can you guess? Of course, it depends, well, on our parameter t. Because for different lengths of our arc, we get different areas of spherical segments. What is
area of sphere?
Yes, of course. So the area is t times, what is the area of spheres? 4 pi?
That's right, it's just S.
Okay.
Yeah.
Okay, I'll write it like this. S of sphere, t times area of sphere. Great. So if we have now some kind of polygonal curve on our sphere, I'll draw another picture. Okay. So a unit sphere, polygonal curve, something like this. And its length is less than pi, as it said in a condition. So for every arc segment of this curve, we can draw its own, well, spherical segment. I'll just draw a couple of them. This is, well, we should intersect, okay. So we have just some spherical segments here. Okay, and well, as far as the length of our curve is less than pi, the area of the spherical segments is less than an area of the sphere itself. So that means that there is some point actually which is not covered by such line segments. And then how to construct a great circle which is not which doesn't intersect our curve using this uncovered point. Guess by this moment the answer should be very clear.
And just take its dual great circle.
Yeah, of course. I'll draw a point here because I guess that's how I get a dual great circle that I need. Okay. Yeah, exactly. So this is how we obtain the required great circle. And problem 7b has actually a similar solution. So a good exercise is to try to figure out the solution without looking into our solutions. So please feel free to try. Do you have any questions about our problem number 7?
So
I guess
it was the solution for 7a, and the solution for 7b is quite similar, but there we should find an area which will be covered more than k times by these segments. Okay.
Okay, so we have 20 minutes left. I'll try to fit in solutions for problem number 9 and problem number 15. Well, actually, problem number 9 has quite similar idea. Let's see. Well, you have a plane, and you have some nails in this plane. What I want to do is actually I want to draw a sphere, as you might wonder. Okay, that's weird sphere, but okay. And then I want to project these nails on my sphere, and I'll use central projection. So just draw a line connecting my nail with the center of my sphere, and then I'll draw a point of intersection. Let's draw it in green here on a sphere. So I do it for every nail. And then if we have some line lying here in our plane, not touching any nails, how would its projection, central projection on our sphere would look like?
It would be a great circle.
Of course, it would be a great circle. Okay, I will try to draw it accurately. Okay, so here is our projection. Okay, and then what I want to do is I want to take our delta of all of my nails and see how it looks like. This is another unit sphere. So all the nails turn into great circles. And these great circles divide our unit sphere into some number of parts. And then our line transforms, well, delta of our line becomes a point, a pair of points actually. Okay, one here and one here. And when the line moves, not touching any nails, what does it mean for this sphere? It means that our point moves without touching great circles. So basically, to find the answer for this problem, we need to understand how much much or many? How much? How much parts are here? So the great circles divide our sphere in some parts. What is the number of these parts? And
I think these parts will be so for each part we have an opposite one, and the dual for the line on the first sphere is a pair of opposite points. So we have to compute not the number of parts, but this
the
number
divided
by
by
2.
Yeah, exactly. Thank you. And well, how to compute this number? Actually, we can do an old trick again. We can project everything on a plane. And great circles become lines. And now our problem is to find how many parts we have on our plane. And I think Andrei already told us the answer. So you just need to tweak it a little bit to get the required answer. But you get the main idea. So this was problem number 9. And now I think, do you have any questions? Okay, let's move to problem number 15, last. It's about jugs filled with water. I have 6-liter jug, 7-liter jug, and 12-liter jug. And it's a very simple problem. You can solve it without any phase spaces. We accepted such solutions. But I want to show you how to actually use phase spaces. So let's see. Well, suppose here we have X liters, here we have Y liters, here we have Z liters. So at the beginning, X equals 6, Y equals 7, and Z equals 0. So the first 2 jugs are filled up, and the second one is empty. And by X, Y, and Z, I think you already guessed that I'll draw coordinates in space. Is X-axis, Y-axis, Z-axis. And an amount of water is actually fixed because you're not allowed to spill it on the ground, and you don't have any source of water to get some more. So it means that X plus Y plus Z equals 13. And as we know from problem number 0 about kids and porridge, these equations means we have a plane, and I'll draw just this part of the plane because, well, obviously an amount of water can be negative, so we need just positive part of this plane. Well, a tricky question. Is this triangle is actually a phase space for our problem?
We can restrict it more.
Of course, because well, you can get more than 6 liters, for example, in this jug. So we need to, restrict it more. Means that X is less or equal than 6, Y is less or equal than 7, and Z is less or equal than 12. And each of these equations means I need to draw, well, for X, I need to draw a plane perpendicular to X-axis, and it cuts the corner of my triangle. And I need to do the same thing for, let's say, for Y and for Z. Okay, I'll draw now this triangle laying flat because it's hard to see what's going on with when it's drawn with the perspective. Okay, let's see. So we have a right triangle and we cut out. Actually, my picture is not quite right because these planes for x and y intersect. So I need to draw something like this, they intersect at this point. Okay, so it goes like this, and this little corner cut out. And let's see, this bottom line corresponds to the situation when z equals 0. This line corresponds to the situation where x equals 0. This is y equals 0. Let's see, this is z equals 12. This is y equals 7. And this is x equals 6. So we start here. And then what can we do? We start here at this point, and we can move in our phase space according to our refills of the juncts. What can we do now? At which direction can we move?
Just one question: if isn't x and y opposite in this, because shouldn't the left side be y equals 0?
Good question. Let's see. So yeah, actually, yes, you are absolutely correct. It, of course, should be. Here we have y.
Looks like we move
Yeah, I just
x
need
and
to
y.
Yeah, I just.
If we reflect the picture, we
Yeah.
obtain this one.
Let's change it for. So we're looking at this triangle from this way. Okay. Thank you for your correction. And which way can we go now? Basically, what we can do when our x is equal to
How the point move in our space if
We can go to the point y equals 0 or x equals 0.
Yeah, of course. This is the point where x equals 0 and z equals 6. Or we can go to this point to correspond to situation where y equals 0 and z equals 7. So what I want to do now is I want to draw a kind of additional lines to help me see what's going on. So I can move along these lines. And they actually should form. They all parallel to the sides of our triangle. They are at equal distance. They should be at equal distance, but of course my picture is extra messy. Well, the thing is, it forms small equilateral, regular triangles. And I can go along these additional lines. Let's see. So if I went this way, then I go here, 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 and here, and so on. So I just travel. And the thing is, I can't stop here, for example. So if I go in some direction, I go there until I hit an edge of a shape. So you may think about it like you have a billiard ball here and you hit it probably in this direction, and it just reflects off our edges. And what we need to do is we need to prove that we can get, well, actually, we can get to any point on the edge. Well, any reasonable point, I mean, with integer coordinates. It is easy to prove if you draw like not messy picture, just see what's going on. the point is we can get to the state where z equals 9, and that's the desired amount of water for a problem. That's the desired state of a phase system, of a phase space, sorry. So do you have any questions? Is it clear how pouring water from one jug to another corresponds to Poincare movement in our phase space?
Yes, yes.
Great. So we have about 5 or 6 minutes left. I guess we have no time to start another solution, but maybe you have some questions. So let's see.
Oh, we can say a few words about the part
Oh yeah.
after the semifinal.
Yes, of course. So as you may see, we published our solutions for part 1, part before the semifinal, and we have a new set of problems. We will publish them this evening. Moscow evening, yeah, thank you. Moscow evening, of course. We will publish them in Mattermost and on our website, everywhere. So you'll get a new set of problems this Moscow evening.
You will have more 3 days to solve them. And the second part is divided into 2 different stories. And I think there are 2 hard problems and some hints for them. So they will be not many problems as in the first part.
But they would be challenging, I think.
And is there a third part?
No.
There is no third part, but you can choose one of the 2 subparts of the second part for you.
It's actually better to choose one because they are huge. They need a lot of effort, each of these parts. So yeah, we'll publish it in Moscow evening.
Можно отдохнуть.
Yeah, if you have any more questions, please ask. I guess we have like 5 more minutes or something. But if not, it was nice to see you. It was nice to, I guess it was nice to read your solutions, right, Andrei?
Yes, your solutions are great, but we cannot see you now without the camera. It doesn't matter.
Thank you. See you later.
See you.
Okay, bye.